Okay, so let's talk about coordinates in astronomy and how we figure out what's going to be up in the sky when so that we can observe it. So this is a real zoomed out view of the Earth. The most standard coordinate system that we use in astronomy is called the Equatorial System. And it's called that because it's basically as if you put a big light bulb inside the Earth and then projected latitude and longitude lines out into the sky. So the lines of declination, we use declination for the equivalent of latitude, are horizontal or are parallel with the equator of the Earth. And so we go from 0 right above the equator up to 90, plus or minus 90 degrees at the North and South Pole. And then we have these, the longitude lines are the lines of right ascension, which is a funky name. A lot of historical names in astronomy, as you're all aware. Of course, the Earth rotates once a day and then also goes around the sun once a year. And so the right ascension, we want to be fixed. We don't want to rotate with the Earth in the way that longitude does. So we have to fix those lines of longitude in some way. And because the Earth is tilted with respect to its orbit around the sun, the position of the sun moves up and down relative to the declination lines over the course of the year. So it's coming up, right? September 21st is the equinox. That's the point where the Earth's axis is tilted. It's not tilted towards or tilted away from the sun. It's tilted kind of lined up with the direction to the sun. And so the sun is exactly on the equator. So it's exactly at declination 0 on the equinox, on both equinoxes. And then in the northern summer months, it goes higher, goes into the north. And in the northern winter months, it goes lower. Now, of course, the sun's not moving, right? And we're not tilting back and forth. We've done this before, I think, right? It's because the Earth is going around the sun and its axis always remains fixed with respect to the background stars. Okay, so a decision at some point in the history of astronomy was made that the 0 point of right ascension would be the point at which the sun crosses the equator on the spring equinox. So the sun is at 0 degrees right ascension and 0 degrees declination on the spring equinox. So that means anything that's near 0 right ascension, you can't see in the spring because it's behind the sun, right? So we actually also have to have the epoch of our right ascension coordinates. So we typically these days use epoch of 2000, the year 2000. But actually it does drift. And the reason it drifts, it would be fixed if the Earth's axis was completely fixed with respect to the background stars, but it's not. We have precession. And that precession, the precession of the equinoxes, moves the point of the equinox 360 degrees in like 26,000 years. So you don't notice it much on the timescale of a few years, 20 years even, right? So we use J2000, the 2000 epoch of coordinates. When I was a grad student in 2000, a lot of people were still using 1950 coordinates, but it was the year 2000. So we mostly rebelled against that as graduate students and insisted on 2000. So maybe we'll still be around for the switch to 2050. That kind of zoomed out equatorial coordinate system, though, isn't really what you perceive when you're standing at your telescope and you need to figure out what's where in the sky. We kind of perceive this alt-az or altitude azimuth coordinate system, where altitude is kind of the angle up from the horizon, and then the azimuth is the angle around the horizon. There is a definition for 0, 0. So 0, 0 is the point on the horizon that's due south. I didn't know that actually until I was preparing this lecture. I don't think it's particularly important, but that concept of an alt-az coordinate system will help. A lot of telescopes are arranged on alt-az mounts, and so kind of work with that. There are some names that are useful to remember, just words. So the zenith is the point directly above you, always, wherever you're standing, right? So the direction that points with respect to the stars changes depending on where you're standing on the Earth. The nadir is the point directly below you. Those are the main things. And then I like this kind of diagram. So I always like to draw this kind of diagram. Actually, I'm going to draw one. This helps me visualize like how things move on the sky. But if you imagine kind of drawing your horizon and then you draw your sky. So that's your zenith. As you probably remember, or just to remind you, the angle that the North Celestial Pole makes with the northern horizon is your latitude. So here we are in Haverford, we're at about 45 degrees latitude, which means it's quite convenient. The North Celestial Pole is always like 45 degrees above the northern horizon. And then I can do my like never eat shredded wheat to add east, south, west. One point that's really useful to remember about the Strawbridge Observatory is that the building was built on a north-south direction. The door by my office to the outside world is north. That's the north door. Yeah, so you can kind of orient your directions. And then everything on the sky rotates around the North Celestial Pole, right? Because the North Pole is directly above the Earth, everything just goes around in a big circle above it. And so you can kind of draw a 90-degree angle and draw your kind of great circle. So a star, or the sun on the equinox, is going to start here due east and go up to its highest point and back down. Right? And in the summer months, you do a longer path across the sky, so longer hours of daylight, and you get higher in the sky. And in the winter months, you have a shorter one. So those are like lines for the sun, but any object, right, is just the same. So if you have an object that is a declination of, say, I don't know, 60 degrees, I can kind of figure out where it's going to be on this. This declination 60 degrees, it's going to be 60 degrees up from my equator line. So that's a right angle. So it's going to be kind of here-ish. And that's an object that's just going to go around in a big circle. My diagram's getting to be a disaster now, isn't it? Sorry. But that's an object that's just going to go around in a great circle around the North Celestial Pole. So we'll never set. Unfortunately, behind a tree some of the time, as viewed from the observatory, but that's life. Okay, so anything that's like, hang on, what's 90? Well, anything that's like 45 degrees declination or lower will rise and set at different times. Anything above those declinations from Haverford is always in the sky. It's just a matter of exactly where. Yeah, so this is talking just a little bit more about right ascension. So it's also, again, saying the 0 point of right ascension is where the sun is on the spring equinox, the vernal equinox. And then it goes around once a year. So the sun kind of moves around through the constellations. The name of the constellations, of course, famously that the sun passes through are the constellations of the Zodiac. The ones that you may know from any astrology interest you've ever had are offset from where the sun currently is in the month that they align with because of the precession of the equinoxes. I think they're offset by like an entire constellation now. Because astrology was like set up 2,000 years ago, so there has been significant precession since then. Also, the official constellations, there's 13 zodiac constellations because there's a constellation called Ophiuchus that also crosses the path the sun goes through. Yes, and I just wanted to also note, there's this funky notation that's sometimes used for degrees in the sky. It's called sexagesimal notation because it's kind of counting by 60s, but also has decimals, I guess. So for example, the coordinates of Betelgeuse, which is the example in the book, it's at 5 hours right ascension, 55 minutes and 10 seconds. So for right ascension, we use hours, minutes, and seconds. The rotation of the Earth carries objects 1 hour in angle across the sky if they're on the equator in 1 hour. That's why it's done in hours. And then sort of equivalently, we also use minutes and seconds for declination. So you'll sometimes see things like 7, 24, 25, 7 degrees, 24 minutes, 25 seconds for declination. And this is going to be one of those things you hate about astronomers as much as magnitudes, but a minute in declination is not a minute in right ascension. There's a factor of 15 between them. So just be aware of that. Yeah, no, sorry. Many modern astronomers now use decimal degrees and decimal for both declination and right ascension, because most of us now just code this into our computer. Right, and then I just included a few other diagrams. We kind of already talked about this, the apparent daily motion of the sun at different times of the year. So the fact that the sun moves up and down in declination, as well as kind of around in a big circle from our perspective relative to the background stars. One of the things that means is that location of sunrise and sunset changes. Don't know if you have noticed that, but it's only due east and due west on the equinoxes. I get to enjoy this from my house because at certain times of year, I can see the sunrise behind the buildings in Philadelphia. That's kind of cool. I wanted to include this thing about estimating angles because that can be useful. So you can use your hand to estimate angles. This works regardless of the size of your hand or the size of you, because most people's hands are in proportion to the length of their arm. So the angular size of the hand is pretty constant. So we do like 10 degrees is your fist at arm length, 1 degree is your pinky finger at arm's length. And then, so the sort of coordinates and time are quite closely tied in astronomy. The book, if you have the book, or if you can have access to the book, or if you'd like me to copy this section, has this whole like elaborate section on time in astronomy. And I could make you like do things like calculate exactly at what time of day certain objects go through the zenith. I'm not going to do any of that because we would these days use a computer to do those kind of calculations. But it's still kind of handy to get, like when you're at the telescope, it's a little bit useful to kind of have a sense of what's where. So I wanted you to have some sense of coordinates. And you'll see, so I thought these were the most important 4 terms about time to make sure that we had discussed or mentioned. So we'll talk about mean solar time, which is the sort of clock time at the center of time zones anyway. That would be the time that you would be using. But apparent solar time differs from that, both because we move within time zones, but also because the orbit of the Earth around the sun is not exactly a circle. So sometimes we're a little bit ahead of mean solar time and sometimes we're a little bit behind it. Sidereal time is the time with respect to the stars, as opposed to solar time. So if we have the sun here, and here is the orbit of the Earth, and here we have the Earth. So imagine there is a person standing on the Earth. 1 solar day is the time it takes for the Earth to rotate once so that the sun is in the same place in the sky the next day. However, the Earth moves around on its orbit while that's going on, right? And it turns out it moves just enough that it takes an extra 4 minutes for us to get back to pointing at the sun relative to where we would be pointing at the stars. So if we have the fixed stars over here, right, going around 360 degrees brings you back to exactly where you were relative to the stars. You have to go an extra 4 minutes in time to point back at the sun. So that sidereal time is the time with respect to the stars, and it kind of codes how the positions of the stars get offset by 4 minutes every day. And then the last definition for us is the Julian date. This is basically a count. Well, this is exactly, it's an integer count of days. Sometimes you'll see decimals because days, you can have a part of a day. The 0 point, I forget when it is, but you can look up when it is. It's a long time ago. So these are big numbers, and it just keeps counting. And astronomers like to use this because then you don't have to worry about which year is a leap year and all that kind of stuff. And so it's kind of gives you a more continuous count of days. So you'll often see Julian date in the logs for time of when observations happen. Whenever you need to convert from a Julian date to a real date, you Google it. That's my advice. Can calculate it yourself if you like. And the book, again, goes through the details of how to do that. There's different kinds of Julian dates. So there's the long Julian date and the modified Julian date. We often use modified Julian date, which resets sometime in the 50s.